Yes, I'm going to talk about algal fossils, and I know several people would say that why would anybody work on algae while there are so many fantastic crawling, running, jumping, biting animals around, even if they are extinct? Well, my answer would be that you have to look closer. These fossils, which I'm going to talk about, come from Estonia, from a small village in central Estonia called Kalania. The locality itself is a working quarry where they quarry limestone and dolomite and crush it and make it into rubble and basically use it for road construction. The layers which I'm going to talk about are of Silurian age. They are Iranian. The conodont data says that they are Prognathus tenuis conodont zone. So basically they are like 440 million years old. The layers which contain exceptionally preserved fossils are actually at the very base of the quarry. So they are like 6 or 7 meters at the bottom of the quarry, and not even in the whole quarry, but actually they can be found in a very small corner of it. In this quarry, the biota is actually everything which you could expect to find in Silurian strata, and in some instances also, in some cases, also those which you do not expect to find in Silurian strata. So there are basically all kinds of invertebrates, and this summer proved that there are also vertebrate fossils around in the quarry. But actually the very first fossils which we found there and which prove that we can see their exceptional preservation are algae. And for a very long time, for several years, we thought that the locality has preserved algal fossils only for some unknown reasons. Well, now we know that it's not true, but nevertheless, the algal fossils are by far the most abundant among the fossils. Here you can see the most abundant fossil species, which is called Levelites hartnageli, and which has been identified as a red algal fossil. But I intended to talk about another algal group, which is called Dasyclad algae. It's a very specific algal group. They are basically green algae. They are unicells, although they are macroscopic unicells, and perhaps even the largest unicellular organisms on Earth belong to this algal group. I know it's hard to believe that they're unicells because some of them show very complicated morphology, but actually when you start to study them, you see that this very complex morphology is made up of fine interconnected tubes. So here is one of these Dasyclad algae, which first got its nickname as Christmas cactus algae because it looks like a bit like an algal version of a Christmas cactus. It's in its life position, it was probably some 8 to 9 centimeters high, kind of bushy-like talus. Up in the left upper corner, you see the part of its internal anatomy. You can see there the central axis and the branching first order laterals and second order laterals, which finally make up the cortex around the entire talus. However, this species does also have an extant equivalent, which is called Cymopolia barbata. My first fossil name was Palaeontological Silurica. And when we compare these fossil specimens and then this recent species, actually the only major difference between them is the presence of a calcium carbonate skeleton on the recent species. Any of the fossil algae in this locality show any traces of any carbonate skeleton. But actually, plasticulate algae are very famous for their fossil record just because of their carbonate skeleton, which has preserved them as fossils. There are some other species which belong to the plasticulate algae, like this beautiful specimen, for instance, which shows beautifully preserved whorls of laterals, at least 3 order of laterals, and reproductive structure at the very top of the chalice. And this species here, which has been named Medusa graptus already a very long time ago, and has also been regarded, as the name also implies, as a graptolite, and has also been included and described in the treatise of invertebrate paleontology, although with a question mark already at that time. But I intended to speak about one very humble species, which has got its name from the locality Kalania, pusilla. The species itself is very small, very humble, absolutely not remarkable at all when you first look at it. It mostly resembles probably some small leaf about 6 or 7 centimeters high, half a centimeter wide. But when you look closer, several specimens reveal its internal anatomy. So here you can see the well-preserved central axis, which runs along the whole talus, and also the whorls of first-order laterals, which are those small piriform structures around the central axis. Several specimens also show the second-order laterals. They are different from the first-order laterals. They are very fine, very hairy, and much longer than the first-order laterals. So on these images, you can see either the whole second-order laterals or the partly preserved second-order laterals on the other image. Many specimens also revealed very peculiar structures. They were like bundles of small ovate structures which were seen along the whole talus. These are structures like the small ovate structures are some 30 micrometers long and 20 micrometers in diameter. Usually they are like around the central axis in small bundles, as I said, and we have determined them as gametophores. So what are gametophores? Plasticulate have 3 kinds of cyst or gamete production modes. So the first type is where the cysts or gametes are produced inside the main axis, which is called the endospore mode and is usually regarded as the most ancient type of cyst production. The second type is where the cysts are produced inside the laterals, and it's called the cladospore cyst production mode. And the third type is where the cysts are produced in specialized structures, which are called gametophores, which is probably the most recent mode of cyst production. So that's probably the type of cyst production which we have in the case of Kalania pusilla. So if we make up the reconstruction of the whole talus, we can see in the vertical section the central axis and the first order laterals which are attached to it, and the second order, fine second order laterals branching from the very tip of the first order laterals, and gametophores which are attached to the first order laterals. The cross section is like a fine flower which shows the central axis, wide central axis, the smaller first order laterals, and again the second order laterals branching from it. But when I forget about these very fine details and anatomy and try to look at this from further at these talus, we see again this absolutely not remarkable club-shaped, very boring small talus like alga. So I'd like to thank all the team at the Poland Quarry and also the team of the students who have collected all these fossils, which we are going to work about for several years, I guess. Thank you.